The project we were given was to create a functioning trebuchet that could launch marbles. We had a little more than a month to design, build, modify, and test the trebuchets. For the design aspect, we had to make a trebuchet fit into a 1 foot by 1 foot box. That being said, we didn't have to have the full trebuchet assembled all at once in the box. So we were given 2 minutes to reassemble the trebuchet to meet the qualifications. Along with the box, we had to make sure that at least 25% of the trebuchet was designed and built using a 3D printer or laser cutter. When building the trebuchets, we were allowed to use any material that we thought would work best, as long as we had approval from Mr. McHugh. The two main restrictions were that it must be a trebuchet and not a catapult, and that the counterweights must be the only source of hurling power. We were allowed to modify the trebuchets in any ways we wanted, as long as we didn't break any of the previous restrictions and it still fit in the 1 foot by 1 foot box. Finally, for testing, we had 2 testing dates, one before the modifications and one after the modifications. To test these trebuchets, we took them to the football field and measured how far they could throw the marble.
Our group spent a few days researching and simulating the trebuchet and searching for possible ratios on the internet before starting to design our own trebuchet. We thought about building one with a wooden outline base, but decided against it after thinking about the barriers on both ends of the trebuchet, possibly preventing a successful runway for the sling and projectile. After coming to group decisions on measurements and ratios, we started to get to work. We decided on a 3/4 inch wooden platform with a thin cardboard runway on top as our base. We cut 2 shapes out of wood to be the main supports. As you can see, there is a triangle connected to a 10-inch post on both sides of the trebuchet to stabilize it, as well as to use the post to put a metal rod through the arm to allow the arm to be able to swing. We mostly stuck with the same idea of the design throughout the whole project with minor changes. We felt that we had done the math correctly and found efficient ratios applicable to our trebuchet. The most critical aspects, in our opinion, were the triangle posts on the sides to stabilize the trebuchet, the drilled holes in our arm and posts for the metal rod to fit through, and the sling. The sling was tied to a pouch, and the fishing line was hot glued to stay together, while the other end of the fishing line was hot glued to the wood at the end of the long arm. We then had another piece of fishing line connected to our pouch, which was shaped like a diamond but pinched and stapled on 2 of the sides. And the other end of that fishing line was wrapped around a small piece of a metal rod hot glued to the end of the long arm. The fishing line wrapped around the metal at the end allowed it to come off at our desired angle, which was roughly 45 degrees. Our group decided to use the Innovation Lab to cut most of our wood. Our group also used the 3D printer to print out a basket to hold our counterweight. We cut the basket right at the top to allow a full range of motion for the swing. The basket was restricting this because the metal rod was hitting this area, so we cut it off. We also cut a hole in the bottom of the basket to allow us to fit one of the weights in upside down due to the fact that both weights have a hook, and it was difficult to fit the rod through the holes of the basket as well as the hooks of the weights. So we inserted a weight upside down to eliminate the possibility of the rod rubbing against the hook of the weights. The basket was efficient for its job, but we thought to try launching the trebuchet without the basket. The projectile went consistently farther without the basket, so we decided to continue launching without the basket. This is our numeric simulation that applies to our trebuchet. As you can see, our potential energy is 3.508 joules, and our kinetic energy is 1.019 joules. This is also our final simulation that led into the design and actual build of the trebuchet.
During the construction process, we had 2 things working well for us. We had good communication, and we had the work divided up evenly among us. For the work, we had 2 people designing the parts and specifications for the project, and we had the other 2 people putting the parts together. For communication, we had told people what each person was doing. We thoroughly explained what was happening throughout the process, and if someone knew they weren't going to be in class for a day, it was said to the group so they could make up for lost work. Some problems that came about during this process are that we spent a while figuring out and changing our dimensions before finalizing it. This caused us to have to go back and change our designs for the basket, supports, and arm. Another setback would be that our basket broke. This caused for one person to be gluing it back together and making sure it was secure instead of assembling the trebuchet or printing off/cutting new parts. The parts we 3D printed /cut out was our arm, our counterweight basket, and the side supports. Some problems with the process overall would be that only one person in our group had the designs towards the very start, and when he was sick, he had failed to share the information with us, which left the group trying to redesign the parts that day in class. We got the designs after the first time he was missing and had better communication sense. Another problem with the process is that we couldn't get the release pouch folded correctly. For this, we had to look at how other groups folded their pouch to get an idea of how to do it.
We actually ended up making our trebuchet much more efficient than we had originally thought it would be. As you can see, at first we calculated our efficiency to be about 11.2%, but our final efficiency calculations came out to be 36.9%. This could be due to the imperfect angle of our release nail, as we weren't able to get it exactly 45 degrees as we had originally designed. It also could be due to any tailwind we experienced during our testing days that helped push the ball farther than it would have gone on a day without wind. Our trebuchet performed fairly well considering the obstacles we encountered, such as when the basket for our weights broke, 3D printing problems, and routing problems. Our arm as a whole was able to swing freely and not bump into or hit any other part of the trebuchet. Our weights also had a free range of motion once they were taken out of the basket. Our basket was the worst part of our design because it took away some of the momentum. The axle we used for our release allowed the marble to come out at a good angle, and it was consistent. If we would have made the arm a little longer and made the height a little taller, we would have been able to throw the marble much farther.